All right, so the next problem 4 is about technology development, and it's a little bit more comprehensive already because we need to incorporate a little bit of economics as well in order to derive profits. But let's first take a look at what the problem is. So consider a firm selling a product with inverse demand function. P demand is equal to 20 minus 0.005 Q. The firm currently has production costs of 10 Q, so that's the variable cost, plus 2,000, which is the fixed cost. The firm has the option of attempting to develop a new technology that would lower production costs to 4Q plus 2,000. So what happens is that the variable cost would go down. And there are research and development costs, and they are 3,315, and if undertaken, must be incurred regardless of whether or not the technology is successful or a failure. So two things can happen. So you develop the new technology and it can be either a success or a failure. If the firm attempts to develop the new technology, their innovation will be successful with probability 9/20 or 0.45. And then throughout your analysis, restrict attention to the profit loss of the firm in only the current period. So it's a one period model, which is to assume that the firm will not be operating in any future period. Okay, so that's just for simplification. And assume that the firm is risk neutral, which is we only care about the expected payoff, or that the firm simply wants to maximize the expected profit. Okay, so let's start first with drawing the decision tree. So let me see if I can create here a little bit of space. So we have a decision, so we have to decide, shall we develop or not develop? And if we develop, Mother Nature may decide that it will become a success. So that's a chance node. Or it will become a failure. Supposed to be an A. Okay, failure. Or we can decide not to develop. And of course, if we do not develop, we will just continue with our existing technology. So that means we don't face the 3,315, and we don't face the 300,315 in development costs. So let me highlight that one. So we don't face that, and all that will happen is, we will work with our demand function 20 minus 0.005 Q and our existing cost function. So how big is the profit? So we need to quickly draw that in Excel. It makes it easier. Of course, we could also calculate it, but I prefer to visualize it. So we have a quantity, Q, and if the intercept of the inverse demand function is 20, then it will intersect at 4,000, because 4,000 times 0.05 will be 20. So we need an x-axis that goes from 0 to 4,000. Okay, so now if you want to highlight that column, you press Shift, Control arrow down, and then you go to Edit, Fill, Series, and you have a step value of 1 and you want to stop at 4,000. So now we can draw the demand function P equals 20 minus 0.005 times Q, and now we can copy this down. So you can copy down with Control D, or if you could also click on this little triangle, on this little square. Okay, so now we have the demand function, and you see that at the quantity of 4,000 we reached the saturation point. But now what's important is we need to look at the different marginal costs. So the existing marginal cost are 10. So I called it marginal cost, I don't know, existing or current. And that is just 10. So we can write everywhere 10. And if things go well, we could have marginal cost. If success, that would be 4. Okay. So what we also need is, we implicitly assume here actually that the firm has this demand function. So because the demand function is downward sloping, we assume that the firm has market power, so the firm could be a monopolist or so. So we definitely also still need the marginal revenue function. And I'll just quickly insert here a column, and I calculate the marginal revenue. And you know the marginal revenue for a firm with market power is always twice as steep as the demand function. So that would be equal to 20 minus 2 times 0.005 times the quantity. But then we tell Excel, because now this will cut through 2000, the quantity 2000, then become negative, and then we have all those negative values but we don't want to display them. So I will tell Excel, if this formula is less than 0, then enter that the number is non-available, but otherwise use this formula. So that means after 2000, the quantity, there will be just NAs. So that avoids that we have all those negative values. So now if we go to 2000, you see that's where the NAs kick in. I think now we have everything in order to illustrate maybe that problem. So let's highlight all the data, insert recommended chart, and let's put that up here. Okay, so now we have here our chart. Okay, maybe let's format it a little bit more nicely so we can better evaluate it. Okay, well, first thing I want to do is maybe delete the chart title. We don't really need that. We can increase the interval on the x-axis, definitely on tick marks. Then we want, let me go to this slide quickly here. Then let's increase maybe the tick marks to, what happens if we do 100, and specify the interval unit to 102. Okay, so maybe let's do 200. Okay, so maybe 400. Okay, so that looks nice. Then let's also format the y-axis, which is the price. And let's put the maximum to 20. And the interval is actually 1. And then let's add grid lines, the vertical ones. Okay, so actually I go back to the specify interval unit 200, because then we can see that currently the firm operates with the high marginal cost. And now I can actually move again here, I guess. And if the firm operates with the marginal cost of 10, the intersection with the marginal revenue is at 1,000, and the firm can charge a price of 15. Okay, so if the firm does not develop, the total revenue is 1,000 times 15. So total revenue, or profit actually, the profit will be 1,000 times 15, so that's 150,000. I mean 15,000. So you see 1,000 times 15, that's 15,000, minus, okay, so now we look at this cost function, so we still have a fixed cost of 2,000, so minus the fixed cost of 2,000, but we also have the variable costs, and the variable costs are 10 for every unit produced, so we have 10 times 1,000, so that's the total variable cost, so minus 10,000. So that means the certainty equivalent is 3,000. Okay. And so now let's move to the development scenario, and we assume that the probability of success is, if the firm attempts to develop the new technology and will be successful, is probability 9 over 20, so that's 0.45. That means it will be not successful, it will be a failure with probability 0.55. So that means we have to, if everything goes well, then we can operate with the lower marginal cost function, and we can see then we will sell 1,600 units and charge a price of 12. That's the intersection. So if everything goes well, the total revenue is selling 1,600 at the price of 12. Okay, so that's the total revenue. And then we have the lower marginal cost. Then we produce the 1,600 units only with marginal cost of 4, so that's 4 times 1,600, so minus 1,600 times 4, which is 6,400, and we still have fixed cost of 2,000. And of course we must not forget the development cost of 3,315. Okay, so how much is this one? So let me use my calculator again. So we enter 1,600 times 12 minus 1,600 times 4 minus 2,000 minus 3,315. Okay, so that gives me 7,485. And if things fail, well, then we basically have to operate still with the old cost function. And in additionally, we have, so in this case, it would make 3,000. But then the 3,315 were in vain. So if things fail, we have what we get under the scenario of not develop, which is the 3,000, but we spent the 3,315 to no avail. So in this case, we just can write this will be equal to the 3,000 minus the 3,315. And of course that is negative 315. Okay, so that would be the decision tree. So the next question is, should the firm undertake research and development efforts in order to attempt development? Okay, so now we need to calculate the expected payoff from development. And the expected payoff from development is equal to 0.45 times 7,485 plus, with a probability of 0.55, we make a profit, or actually a loss, of 315. Okay, so now what do we get? 0.45 times 7,485 plus 0.55 times negative 315. Okay, so now I get 3,195. Oh, I did make a mistake. Well, and since this is expected payoff is greater than the certainty equivalent of not develop, the answer is, of course, we will develop. So the answer is develop. Okay, so next question. Suppose instead that research and development costs are 4,095. So should the firm undertake research and development efforts in order to attempt development of this new? Okay, so now we have a new scenario, which is instead of having 3,315, we have 4,095. Okay, so now we can basically just replace these numbers here. So now we have here 4,095, and here we have 4,095. So that means here it is easy, so we get right away a loss of 1,095, and for the success scenario we will get 1,600 times 12 minus 1,600 times 4 minus 2,000 minus 4,095. I get 6,705. So now we get 6,705. Okay, so now the expected payoff becomes so now we have a new expected payoff of develop, which is still with probability 0.45, but now we make only 6,705, and with a probability of 0.55 we make a loss of 1,095. Okay, so now the question is this still more than 3,000? Probably not, but let's check. 0.45 times 6,705 plus 0.55 times negative 1,095, and now I get 2,415. Again, I hope I didn't make a mistake. But under this scenario, we would now, the conclusion, the decision would now be not develop. Okay, so suppose instead that research and development costs are 4,095 and that innovation will be successful with P equals 23/40. Okay, so now the only thing that changes is we have now new success and failure probabilities. But we still have the 4,095, so the payoff stay the same. The only thing that changes are the probabilities. And so now we assume that the probability of success is 23/40. And the probability of failure is 17/40. So that means the new expected payoff is equal to the expected payoff from development, of course, (23/40) times 6,705 plus 17/40 times negative 23/40 times 6,705 plus 17/40 times open parentheses negative. Okay, so now it is 3,390, and that is again higher than or greater than the 3,000. So in this case we would develop again, because what happened is that initially we have now a higher probability of success, and now developing is again more favorable. Okay, so yeah, that's it. So that was a little bit more complex. That also linked again to some economic theory, but once you've figured out how to calculate the profit, it's actually pretty straightforward. Okay, so let's just stop here and then continue with another problem in the next video.